In this video, I'm going to walk you through the steps involved with calculating or performing a one-sample t-test from the approach of 95% confidence intervals. And that's the first approach I describe in the textbook. The steps involved amount to 8 steps, and I mentioned in a textbook that seems like a lot of steps, but a few of them are pretty simple to execute, so it's probably not as laborious as it seems. So here are the steps. Calculate the sample mean and standard deviation. That's covered in the descriptive statistics chapter. Calculate the difference between the sample mean and the non-sample mean. That's a pretty simple thing to do. Calculate the standard error of the mean. Calculate the degrees of freedom. Easy. Identify the t-value from the t-distribution with specified degrees of freedom. It's exactly the same approach used with identifying the confidence intervals for the standard error of the mean. Multiply the t-value and the standard error of the mean. Same thing. Add and subtract the product from step 6 to and from the result from step 2. So step 2 is the difference between the sample mean and the non-sample mean. And then you add and subtract what you get from step 6 from that difference between the sample mean and the non-sample mean. And then finally step 8 is an interpretation of the result. So step 1 is, I'm not going to repeat how to calculate a mean and a standard deviation here. I'm going to assume you know how to do that. The mean was 7.31 and the standard deviation was 1.06. Now this was hours of sleep based on a sample of 10 people. So 10 people provided estimates of how long they sleep at night or within a 24-hour period, and the mean came out at 7.31 and the standard deviation was 1.06. So step 2, the difference between the sample mean and the non-sample mean, or sometimes called the population mean, amounted to negative 0.69. So you'll recall from the textbook, I had a hunch that the number of hours people sleep per night on average is 8 hours. But the sample, based on 10 people, suggests that it's 7.31. That's the point estimate. We do not know if this point estimate is statistically significantly different from my hunch, because sampling variability can easily cause a mean of 7.31 to arise simply by chance, even though the population is really an 8.00. So we need to do the one-sample t-test to actually find out what are the chances of that. Well, step 3, we need to calculate the standard error of the mean. And in this case, it's the standard deviation divided by the square root of 10, which gives a standard error of the mean of 0.34. Step 4, easy, degrees of freedom, always n-1 in the one-sample t-test case. And in this example, 10 minus 1 yields 9. Then we have step 5, which involves going to the Excel function to estimate the critical t-value, if you will, from the t-distribution with 9 degrees of freedom and 95% confidence. So that 0.05 was determined by subtracting 0.95 from 1, because the way the Excel function works is that it wants you to identify the percentage of observations that exceed a point within the distribution. So it's at the tail end of the distribution, not the middle of the distribution. And when this function is actually inputted into SPSS, 0.05 with 9 degrees of freedom, and we get 2.26 as the critical portion of the t-distribution that demarcates 95% from 2.26 to negative 2.26. So that's 95%. Values in excess of 2.26 are very rarely observed. 5% or less of the observations should be observed in the t-distribution with 9 degrees of freedom. And so the next step was to calculate the product, which here's that t-value I obtained within the t-distribution, and I'm multiplying it by the standard error of the mean, and that gives a value of 0.77. So now I'm at the home stretch. I've just got the upper and lower bound that needs to be calculated for the difference between the means. Recall that from step 2, calculated the difference between the sample mean and the non-sample mean, and that resulted in negative 0.69 all the way over here. And now I want to calculate the 95% confidence intervals associated with that difference between the sample mean and the non-sample mean. And by subtracting 0.77, which was obtained at step 6, I get negative 1.46, and the upper bound, and this is crucial, the upper bound actually intersected with 0. It actually is a value of 0.08. And because the confidence interval associated with the difference between the sample mean and the population mean, or the non-sample mean, because one value is negative and one is positive, this implies that with 95% confidence, we cannot reject the null hypothesis of no difference between the sample mean and the population mean. So basically, what this means is that my hunch of 8 hours per night cannot be disconfirmed with this sample of 10 individuals when I specify 95% confidence as the demarcation criterion that needs to be observed in order to abandon my hunch as probably not the case. So my hunch is safe, basically, with the sample size of 10. Now, as you proceed to the textbook, you'll find that if you did the analysis with a larger sample size, things get a little bit different, and I encourage you to check that out.